Without further ado, let me introduce today's speaker, is Sergei Gukov. His title is Rokhlin, Quantum Groups and BPS States.
Thank you very much. So let me know if screen sharing works.
Perfect.
Yes.
Good. So first, I want to thank Sheldon and all the organizers of the series for making this events possible. At least for me personally, they made this difficult times less difficult. So I really enjoyed many talks in the series from before. I also want to thank my collaborators. I'm humbled and proud to be part of this wonderful team shown here. And this talk will be based mostly on 2 papers listed here that I recommend checking for further details and technical points. In this talk, I'll try to be as simple or non-technical as possible, and hopefully it will be somewhat entertaining. After all, this is supposed to be a colloquium talk for a broad audience. Let's see if I can advance the slide. Let me try to start again. Sorry about this. So let's see if this works. Here we go again, and full screen mode. So let's see. Yes. So it's hard to be simpler than a harmonic oscillator. So I'll try to stick to my promise to be simple and entertaining in this talk. And this is not actually a joke. So what we'll be discussing are quantum systems, and aspect of harmonic oscillator that will be relevant to us is its spectrum, which is basically consists of integer spaced levels. And we'll try to organize spectra of quantum systems like this in a generating function with a variable q, so that if you put it together, then for harmonic oscillator, you get this nice Q series, which has integer powers, integer coefficients, and the only fractional power of Q you see is the overall factor, which has to do with the ground state energy of the harmonic oscillator. A wise man once said that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. So this quote is especially relevant to our discussion today, because even though the spectra that we'll be talking about will come from quantum field theories and string theory in higher dimensions, at heart, these are basically same quantum systems as harmonic oscillator. In fact, an example of a spectrum presented in this form of a Q series is shown in the bottom of the slide. And my goal today will be to be, again, as simple as possible, but also as concrete as possible. So I'll give you very hands-on concrete tools how to compute a spectrum, such as the one shown on the bottom of the slide. So I'll try to explain this later. And the spectra that we'll be talking about are putting together particular states in a quantum system. In physics, they're usually called BPS states. These are some kind of extremal or minimal states, in the sense that they're trying to minimize some function or functional, for example, total area or some energy function. And not always, but in many cases, this special so-called BPS states have nice geometric interpretation. They can be understood as minimal area curves or solutions to very nice partial differential equations and so on. One well-known example of BPS Q series with all the features that I already mentioned appears from Vafa-Witten theory. That's a topologically twisted n=4 superring Mills that can be defined on any 4 manifold. And it produces a Q series of the form that we saw earlier, or that we see in the bottom of the slide, and has a couple of features that will be relevant for us. So first, Vafa-Witten partition function gives you not just a single Q series, it gives you a collection, several Q series for a given 4 manifold, which are labeled by what physicists call Hooft fluxes. Another interesting feature, which also will have some bearings for our discussion, is observation that goes back to work of Nakajima in the early 90s, that this Q series happens to be a character of some vertex algebra or equivalently chiral conformal field theory. So what we'll discuss today is best viewed as a three-dimensional analog of Vafa-Witten theory. In particular, it will share many of the same features. It will be a Q series where variable Q will be understood as a parameter of the quantum group, and it will be assumed to be generic. Just like Vafa-Witten partition function, it's actually not a single function, it's rather BPS partition vector, meaning that it's labeled by elements of H1 or better yet, spin C structures on a given three-manifold. I won't talk about this today, but it also has interesting connections to chiral algebras, modular properties, and so on. This won't be subject of my talk today, though. And finally, last but not least, I'll try to explain that it's very computable, especially compared to the Vafa-Witten theory, and very easy to play with. So that's going to be, in some sense, the main message of the talk today. So by now, this BPS Q series invariance that I'll be describing developed into a fairly rich story, and perhaps you have heard some aspects of this story before in various talks. If you did, that's good. What I'll do today hopefully will be complementary and will provide more complete, broader picture for this discussion. If you haven't seen this before, that's also fine. I'll try to make this talk self-contained. And as I mentioned earlier, I'll give you all the necessary tools required to actually compute such Q series in concrete examples like the one shown in the bottom of the slide. In fact, let's start with our first example. To get to the first example, we'll go to the 19th century. And just like in physics, I wanted to emphasize that what we'll be discussing is a glorified harmonic oscillator, namely spectra of quantum systems, analogous to harmonic oscillator. The math counterpart of a harmonic oscillator is probably a Dedekind eta function. It's the simplest building block of modular objects, and also has the form of a Q series, in fact, of the same form that we saw before, with some fractional power of Q in front, and then Q series with integer powers, integer coefficients, and so on. When we first encounter the Dedekind eta function, we probably encounter it in the form of infinite product. But then, of course, we can expand it into a sum, and then we notice that the exponents of the powers of Q grow quadratically. So therefore, you can actually rewrite it as infinite sum, not just infinite product, with coefficients which are either +1, -1, or 0, depending on whether index m in the sum is 1, 11, 5, 7, modulo 12. So there is this interesting congruence mod 12 that appears. And other than that, it looks very much like a theta function in the sense that it's Q to something quadratic. Well, on this slide, for some reason, I have a picture of the trefoil knot. And I don't know if Dedekind knew about trefoil knot. He certainly didn't know about Alexander polynomial of the trefoil knot, which was introduced 50 years later by James Alexander II, who spent most of his career at Princeton Institute for Advanced Study. And the Alexander polynomial can be defined in many different ways. It also is an example of a counting problem. But perhaps the simplest way of defining it is using the skein relations shown here. And if we start with initial condition that for unknot, the Alexander polynomial is equal to 1, then the skein relation allows you to compute it for any other knot. So here's a small table which illustrates Alexander polynomial of trefoil knot, figure 8 knot, and 5-2 knot. It's a Laurent polynomial in X, fairly nice, fairly simple, and has many, many interesting applications in topology. So why did I put the picture of trefoil knot on a slide which had Dedekind eta function? They seem to have very little in common. So to answer this question, let me stop sharing, and I'll use the same Alexander polynomial of the trefoil knot that I had a second ago, and instead I'll share with you a mathematical notebook just to illustrate how simple the calculation is that I'm going to do. So hopefully it will work. Do you see the mathematical notebook? It's so far completely empty. So what I'll do, I'll try to expand in a series the inverse of Alexander polynomial of the trefoil knot. Here in the numerator, I'll put a very simple factor x minus x inverse, but more importantly, in the denominator, I'll put the Alexander polynomial of the trefoil knot, and I'll ask Mathematica to expand it in real time for us near x equals 0, say up to 40 coefficients or power 40. And notice if you look closer, so let me maybe try to amplify this. I'm not sure if I can. I'll try to make size a little larger. Oh yeah, it worked. So what you see here is the same congruence mod 12, namely coefficients are plus minus 1, just like in the Dedekind eta function. And you see 1, 5, 7, 11, then 13, 17, 19, and the signs and everything goes exactly as in the case of Dedekind eta function. So that's kind of neat, right? So let's go back to original slides. So I'll share again the main file. Here we go. So after all, there is something that Dedekind eta function and the Alexander polynomial of the trefoil knot, or rather its inverse, have in common. Namely, they have in common same coefficients. Here on this slide, I call them epsilon m, and these are precisely this plus one or minus 1 modulo 12. So one has a series in Q, the other is expansion variable x. For Dedekind eta function, the power grows quadratically. It's roughly m squared over 24. And for inverse Alexander polynomial, it grows linearly. So these are different variables and so on, but coefficients are the same. So a natural question is, can we combine it together? So we'll keep the same coefficients. And basically, for each term labeled by m, we'll write both power of q, which is quadratic in m, and power of x, which is linear in m. So we get something in two variables. We basically married Dedekind and Alexander together in this two variable series. And question is it just a neat example? It's a very simple calculation we did with Mathematica, or is it something a little bit more meaningful that exists for general knots? So that's a question we'll try to answer next. Another interesting point that we'll try to answer is that in the study of modular forms, the variable is always called q. So modular people call q exponential of 2 pi I tau. And remember, I told you that we're going to study BPS Q series, where Q will have to do with quantum groups, which in theory of quantum groups is also called Q. So another obvious question is, first of all, what does this function have to do with BPS Q series? And more importantly, is Q used in Dedekind eta function really the same Q that we call by the same letter in the theory of quantum groups, or this is just an accident and there is some relation between the variables? Okay. Any questions so far?
We have a question if the series, question from Greg Moore, if the series F31 converges, that doesn't converge?
No, it's in this case, it has better convergence properties than in more general cases. Of course, I wouldn't be asking this question if there wasn't an analog of the series for more general knots. And for more general knots, so for trefoil, there are several special things that happen. But for more general knots, it's going to be much more complex. It will have very poor convergence properties. And the way to think about it, the precise statement, is that you look at a given power of x. So it's a formal generating function with respect to x. You look at a given power of x, and the coefficient will be some Q series. In this case, it's just a monomial. That's why it's horribly simple. But in general, you look at that coefficient at a given power of x, and that will be a convergent Q series. So that's the precise statement. But again, we're pretty far from that. So let's try to answer these questions, namely whether they have anything to do with quantum groups, and if Q in the Dedekind eta function has anything to do with Q in quantum groups. As I promised, I'll try to be as simple as possible. I'll try to avoid as many technical details as I can. So in particular, I'll focus just on the case of SL2. There is, of course, a generalization of this story for other carton types, but I'll just talk about SL2 today. For SL2, the quantum group, a generic Q, is defined in a fairly simple way using Chevalier generators E, F, and K, and the relations written here on the slide, where again, Q is assumed to be generic. Suppose we want to take Q, which was generic, say, inside the unit circle, to root of unity. That's where things will get a little bit interesting. In particular, the story will be slightly different depending on whether the order of this root of unity is even or odd. Suppose the order of the root is even. I'm going to call it 2p in this case. So then you can check that these general relations for quantum group at generic Q are actually consistent with additional relations that require K to be unipotent and E and F to be nilpotent. For example, if you look at the first relations in the top of the slide, this conjugation of E and F by K, if you repeat this conjugation P times, you see that on the right-hand side, you get Q to the power 2P. But if Q is a 2P root of unity, then that's 1. So therefore, it tells us that setting K to the power 2P equals 1 is fairly consistent, and so on. So what we get is an object that's called a restricted quantum group. It's a version of a small quantum group introduced by George Lustig, also called finite quantum group, and it has several other names in the literature sometimes. And part of the reason is that this object that we obtain by imposing these additional relations is actually finite dimensional. So in this case, dimension of this restricted quantum group at 2p root of unity is 2 times p cubed. So that's a very neat fact, which makes it extremely attractive for people who like to study quantum groups. Well, the center of this finite restricted quantum group is also, of course, finite dimensional. In this case, its dimension is 3p minus 1. It grows linearly with the order of root of unity. So that's not terribly surprising. What is surprising is that the center carries representation of SL2Z. In other words, there are S and T matrices associated with the center, and this happen to be S and T matrices of logarithmic vertex algebra. This logarithmic vertex algebra is a non-rational CFT. It's logarithmic, it's non-unitary. And in this particular case, when we talk about 2p root quantum groups at 2p roots of unity, the relevant logarithmic vertex algebra is so-called triplet 1, p model. It's close cousin of minimal models pushed into non-unitary regime. So this relation between and this modularity that is surprising and is highly non-trivial that we see on the center of quantum group is actually a variant of more general philosophy that or relations between quantum groups and chiral algebras that goes by the name of Kazhdan-Lustig correspondence. And perhaps more familiar versions of Kazhdan-Lustig correspondence appear in the context of fractional conformal field theories, where the corresponding representation, SL2Z representation, would be the so-called Verlinde representation. We encounter them in physics in the study of WZW models. Verlinde representation is part of this bigger SL2Z representation that we encounter by looking at the center of this quantum group at even root of unity or related to the triplet model, and various details you can find in some of these papers that I mentioned here. So the two are related by operation called semi-simplification. This is where the plot thickens. There are many interesting details that go now, or directions in which you can go. And in paper from several months ago, as well as in the current work, our motivation, or at least part of our motivation, is to produce analog of this table, which in particular involves SL2Z action on the center of quantum group and its relation to various logarithmic vertex algebras for other Cartan types. It has to be noted that even the dimension of the center of quantum group for other Cartan types is not known in a closed form at present. So there is no easy formula. And this is obviously a prerequisite if you want to study SL2Z action on the center of the quantum group. So therefore, going to high rank is extremely interesting. And again, that was part of our motivation, but there is a lot of unknown stuff in that territory. That's partly why it's interesting. Even if we limit ourselves to SL2, there are lots of additional choices and details as well. For instance, remember we had to make a choice whether we talk about root of unity of even or odd order. And this actually makes quite a bit of difference. So far, I was talking about roots of unity of even order, but we could have talked about roots of unity of odd order, which is also quite typical in the study of small quantum groups. Aside from this binary choice, there are other choices. For instance, if we talk about odd root of unity, we could consider several variants of quantum group called small quantum group. In his original paper, George Lustig called them U and U tilde. One would be of dimension k cubed, where k is the order of the root of unity. The other would be of dimension twice k cubed. And here I mentioned only one of them, one of these two choices. Similarly, if we talk about even root of unity, just like we did before, we could have also additional choices. We could include or not include square root of the generator k in our algebra, and that would result in two different versions, both of which go by the name restricted quantum group. In fact, one was considered by Kondo and Saito, the other was considered by Murakami and Nagatomo, and these are quite different quantum groups. In fact, they have different properties. So as you can see, the plot thickens, and I didn't even mention the Langlands duality, which in the case of SU2 relates SU2 and SO3. So if you talk about lattices, for example, if you try to construct a triplet model and other logarithmic vertex algebras based on lattices using kernels of some screening operators, you have a choice whether you talk about SU2 or SO3 weight lattice. So if you find yourself in the candy store of quantum groups, there are lots of flavors to choose from. And if you want to specialize in this area, then it's easy to get addicted to the subject. You basically see that there are lots of extremely interesting details, and you probably want to get more and more of this. After all, that's why you come to the candy store of quantum groups. But if you're not a specialist in this area, you probably start thinking that I'm getting carried away by the technical details, especially since I promised you that the talk will be less technical. So indeed, that's true. I apologize, I got carried away a little bit, but I wanted to show you that there are many different variants, and I did want to give you a glimpse of many different flavors of the story, which was indeed part of our motivation. But more importantly, you probably also wonder what this has to do with BPS Q series. After all, we didn't get much closer to this BPS Q series or to the two variable series that we produced in the case of trefoil knot by marrying the Dedekind eta function and the inverse Alexander polynomial. In those expressions, the variable Q was generic. After all, I told you it was supposed to be just generic root of unity, generic Q inside the unit circle. Whereas here, I quickly started talking about roots of unity. So if variable Q is relevant, it's root of unity here. And the second variable that was variable in the Alexander polynomial that we call X is not even inside here. So I didn't even, in this case of quantum groups, we don't even have the variable X yet. So it looks like we're pretty far from where I want to go, but this is not quite the case. Actually, the answer to both of these questions is just around the corner. So maybe that's another good question to pause if there are any questions.
There was a question about the how the SL2 action on the center generalizes to G equals SLN.
I don't think that's known. Actually, that was precisely our motivation to produce it for other carton types. I don't think it's known even for it's not known for other SLNs. Our work implies, for example, that for SL3, instead of 2 copies of Verlinder representation that you saw in the case of SL2, you'll have 10 copies of Verlinder representation and so on. So it has interesting connection to various geometric structures that appear, but I don't think it's known. So that was precisely the motivation.
Another question just came in. How are these different versions in the candy store of quantum SL2 the same? Are they equivalent graded Manuelo categories of representations?
I didn't want to talk about categories at all. So like I said, I promised to keep this talk extremely simple. So I'm glad I motivated people to look at it. So they're not the same. First, they're not the same. There's a different flavors in candy stores. And B, they actually have completely different properties. So some of them braided and have nice R matrices, some are not. So examples are illustrated here. So again, if you want to specialize in this, I'm glad I set you on the right path. But indeed, I didn't want to mention the word category ever in my talk today to keep it simple. Basically, harmonic oscillator, Dedekind unity function, that's roughly where I want to keep. Okay, so the answer to these questions, what does any of these have to do with BPS Q series? Namely, what's the link between these quantum groups I told you about and BPS Q series, or this two variable series, involves additional ingredient. And this ingredient was introduced about 30 years ago by Akutsu, Deguchi, and Otsky. So in their work that's shown here, they introduced a sequence of polynomial invariants of knots, one for each natural number n, which could be 2, 3, 4, and so on. And these polynomial invariants are close cousins of the Alexander polynomial. So I'm going to write them in using the same variable x that we used to write Alexander polynomial. And this was very interesting work. So it was introduced, again, about 30 years ago for its relevance or analogy with Alexander polynomial. Sometimes these invariants are called colored Alexander polynomials. They're also often in the literature called ADO polynomial invariants. So they were, even though the history is pretty long, like I say, it's almost 30 years, somehow they were not very popular in theory of quantum group invariance and otherwise. So they basically remained a little bit outside of the spotlight in both quantum topology and in various other topics. For instance, we searched really hard when we were working on this paper from several months ago, and until this year, we couldn't find any single paper in physics that would mention this ADO polynomial. So in particular, there was no physical interpretation or, in fact, any kind of physical discussion. However, there was one person who was quite committed to the subject, Jun Murakami, and there were several people, no, not just him, but Jun was definitely one of them. He was already mentioned in this original paper by ADO, so it's reference 15 on the slide, and he did some related work just around the same time. So he in fact was doing very closely related work to this ADO polynomials. And here is another paper by Jun Murakami from 16 years later. Like I say, he stayed pretty committed to this topic, where he says that here we redefine this invariance, meaning ADO invariance, using the quantum group. And he talks about quantum group at even root of unity. In fact, you see same relations I wrote before. So the upshot is that this ADO polynomial invariants are related to quantum groups at even roots of unity. So that's what I want you to take away from this. Jun Murakami, whose name I was already mentioning in several of the previous slides, is quite well known for his work on the volume conjecture. In fact, that work involved both Jun Murakami and Hitoshi Murakami. And the typical joke in quantum topology goes by saying that these two Murakamis are not related. So that is fairly well known. But something that I didn't know is that they're actually pretty much of the same age. So they're from the same year. In fact, 2 years ago, I went to a birthday conference. It was a double-header birthday conference celebrating 60th year anniversary of Jun Murakami and Hitoshi Murakami together. And I remember Jun Murakami gave a very nice talk where he talked about this work and other related logarithmic knot invariants, mentioning ADO invariants and so on. And I remember I was sitting there in the audience and thinking precisely about this question: what would be its connection to physics? At that time, I was working with Ciprian Manolescu on two variable series in terms of x and q of a kind that I showed you earlier. And I was wondering, it would be nice that if it was some connection between these objects, and that would be, of course, a pity if this ADO polynomials and other logarithmic invariants, which remained by that time at the outskirts of quantum topology, had no connection to physics, would remain outside of physics. So here is the explicit expression of this ADO polynomial invariance for simple knots. And again, they're labeled in addition by integer, which you can think of as order of the root of unity. So the leading non-trivial polynomial is basically the same as Alexander polynomial, but then you get close cousins of Alexander polynomial in this variable x as you would go further and further. So surprisingly, the connection is extremely simple. So for instance, in order to obtain this ADO polynomials for the trefoil knot, you can take that series, that function in two variables, x and q, and simply set q equals root of unity. And I promise you that depending on your choice of root of unity, you're going to find precisely one of these ADO polynomials. So to get from that two variable series, which involves x and q, all you have to do is to set q to root of unity. In fact, there is a same story or similar story for every knot. And the reason it comes about is that there is indeed this, so now I'm coming to this BPS Q series, that for every closed manifold, there is a BPS Q series invariant or collection of invariants, which is can be defined in physics in various ways. For example, originally it was defined using 3D correspondence as a half index of 3D n equals to theory T of M3. You can also define it as a Rosansky-Witten theory with a target space, which is cotangent bundle of affine Grassmannian, say for SL2, if we work with SL2 today. And if you specialize your three manifold to be a knot complement, you get precisely the two variable series, which for the trefoil knot we already saw before. So that's going to be exactly the two variable series. But the point is that there should be analogous thing for any knot, not just trefoil knot. And the variable x, which is second variable aside from q, has to do with boundary conditions, namely its eigenvalue of the meridian holonomy on the knot complement, very much like what we see in various versions of volume conjecture and so on and so forth. Now, if you want to find concretely this invariant f of x and q for knot complement, first you can use any of the physics definitions that I mentioned, and that's how some of these invariants were computed in early days. But what you can also do is to use some of the structural properties that come from physics and take them as your definitions. So for instance, in the very beginning, we saw that for the trefoil knot, the way we constructed this two variable series was basically as a Q deformation of inverse Alexander polynomial. And this fact is a structural property for any knot, namely as Q goes to root of unity, or to Q goes to 1, f of xq is supposed to go to one of the Alexander polynomial. Other set of properties that I already mentioned is that if q goes to other roots of unity, you're supposed to find ADO polynomials, or to be more precise, the ratio of ADO polynomial divided by Alexander polynomial. So that we already mentioned before. Another property which was very useful, and in fact pretty much the only one in early days of this story, is the fact that if you expand this f of xq near q equals 1, you get a set of Vasiliev invariants. So from that perspective, you could say that this two variable object is actually a repackaging of Vasiliev invariants into new concoction that basically transfers its domain of expansion from q equals to 1 to q equals 0, if you want to write this as a Q series. And this was very useful property in early days. Even this repackaging of Vasiliev invariants can be turned into productive constructive machinery to construct this f of x and q. But as soon as it was realized that it's annihilated by q difference operator, namely the quantum A polynomial, that technology became much faster and much easier. So there is another property that I mentioned in the bottom of the slide, that this two variable object is killed by what's called quantum A polynomial. This has to do with quantization of SL2C flat connections and so on the knot complement. So now you get lots of properties. They all come from physics, and now you can take any combination of them. They're actually over-constraining as your favorite definition, a way to produce this two variable object f of x and q. So for instance, you can take combination of Q difference equation with initial conditions set by ADO polynomials at roots of unity. So that could be one particular way to produce it. And then other properties you can use as checks to verify that the additional properties hold. So that's not all. So you can use any of these techniques. There are additional ways. For instance, there was very nice work by Sanyuk Park recently this year, which provided yet another way of computing this two-variable object f of x and q in terms of quantum groups at generic Q. Here, Verma modules play an important role. And aside from being very promising for conceptual developments of the subject, this work also provided very nice computational tools. In particular, here it quickly covered various cases such as fibered knots and double twist knots and so on, which you can see in the outline of the paper. So this is a table of knots up to 7 crossings. And when this BPS Q series invariants were introduced, basically the two-variable object that I'm describing for you was only known for the unknot. And our work with Chypre and Manolescu focused on producing this f of x and q for torus knots. And we managed to do one hyperbolic knot, namely the figure 8 knot. And at first, like I say, we were using basically repackaging of Vasiliev invariants. And once this Q difference equation coming from a polynomial came to the stage, it became a useful tool. So that's what helped us to do figure 8 knot. But back in the day, I thought that doing next knot, namely 5-2 hyperbolic knot, would be extremely difficult. So we didn't even try. But and therefore there would be lots of gaps in this table for which computations would be hard. But this technology based on R metrics and quantum groups from paper of Park allowed to cover lots of cases. And as you can see, basically fill many of the gaps here by producing some statements for this other knots. And there are still quite a few question marks for which this two-variable series in explicit form is not known or hasn't been looked at. There are tools available, so any of the methods I just mentioned would be quite useful, and it would be good to tackle them, namely this knot 6-2, 6-3, 7-6, not only for academic reason, but also because this two-variable series is basically a fuel for constructing BPS Q series for any closed three-manifold. So I'll try to describe that next, but maybe I pose for questions here.
I think you can continue.
Good. So the basic idea is that this two-variable series is indeed like a fuel for building Q-series invariants for closed three-manifolds. As I mentioned, the variable x in that two-variable object labeled by that depends on x and q has to do with the boundary condition, namely with the toral boundary of the knot complement. So if we want to cap it off, the three-manifold, then the knot complement into closed three-manifold, then the variable x will disappear. And there is a surgery formula, basically cut and gluing technique, that allows to produce closed three-manifolds from diagrams of knots and links. So that's what's underlying this construction. This theorem, which is due to Licorice and Wallace, says that every closed-oriented three-manifold can be constructed as a surgery on a framed knot or link. And moreover, the constructions which give same three-manifold from different framed knots and links are related by Kirby moves. So that's why I add the name of Rob Kirby here. And because every three-manifold can be constructed by this cut and gluing technique, namely surgery, it's important to know the invariance for knots and links. So that's why I spent quite some time delving on this invariant that depends on both Q and X. Now, all you need, once you have this invariance for knots and links, you need a Sergei formula. And I'm not going to show details of the Sergei formula, it's not relevant. It's basically taking that two variable thing that depends on X and Q and takes a convolution with a kernel that's very simple, very universal, and only depends on the Sergei coefficient. For instance, if I want to do a Sergei on a figure-8 knot with a rational coefficient such as 4/17, I basically have to take a convolution of that universal kernel that depends on the Sergei coefficient with two variable series for the figure-8 knot that we discussed a moment ago. So that allows you to produce invariance for closed manifolds where the variable X is gone, but variable Q still stays there. And again, morally has to be thought of as quantum group variable or parameter inside the unit circle. So once you have this technique, you can actually start checking that, first of all, what you got is a topological invariant. Like I said, it's important that to know that different ways of constructing the same manifold produce for you the same Q series. For instance, the first example shown here on the slide is a manifold which can be constructed as a negative Sergei on a trefoil knot, as well as a positive Sergei on a figure-8 knot. It's the same manifold. And these two ways of presenting this manifold are related by Kirby moves. So you can independently compute the two variable series for trefoil knot and for figure-8 knot and simply check that the result of the Sergei is the same. So here I can write it in a closed form. So it's going to be the z hat of Q written as a Q hypergeometric function. So that's already quite important, and it shows, so it allows you to do the checks on a topological invariance. And this is kind of thing that I personally would like to have in the case of Vafa-Witten theory. So in Vafa-Witten theory, we also produce invariants for four manifolds, which are Q series invariants, very much like in this case. But there is no non-trivial example where we can check Kirby moves, simply because we don't have enough technique in Vafa-Witten theory to produce Vafa-Witten partition functions associated to Kirby diagrams, which are also knots and links, just like here, but they're describing four manifolds. So in that sense, this three manifold version is a little bit easier to play with. In particular, you can check Kirby moves and other operations. So the second example on the slide illustrates that it works for manifolds with any structure. So this is a hyperbolic manifold. It's not ciphered, not anything special. It's some random Sergei on a figure-8 knot. And as such, it produces for you a Q series, which you can compute explicitly using these techniques. So here I show the coefficient of Q to the 500. It's 15,040. I have no idea how to write this Q series in a closed form, for example, in the form of a Q hypergeometric function, as in the first example. And I offer maybe a bottle of wine or a case of wine to anyone who can do it. So this technique allows you to produce Q powers or coefficients of Q powers to any order you wish, but we have no idea how to write it in a closed form, and that would actually be useful for various applications. So what is this BPS Q series of closed three manifolds good for? Honest answer is I don't know. It's still fairly new. So my feeling is that best uses and applications are still waiting to be found. If we treat it as a function of Q, then it produces very interesting functions with peculiar modular properties. In fact, Miranda Chang in her talk in this series focused precisely on this aspect. So you can think about this Q series invariance as a factory for interesting mock modular forms, high depth mock modular forms, or quantum modular forms. So this is one aspect. Another aspect is that, of course, it depends, this answer depends on the choice of a three manifold, so it would be nice to use it for topology one way or the other. And it also depends on choice of these additional labels. which are elements of H1, or better yet, choices of spin C structure on a 3-manifold. So that's the aspect that we usually try to suppress, for example, by choosing 3 manifolds which have trivial H1, where there is no label B to worry about. But actually, in the remainder of my time, I want to focus on this spin C structures and ask, how does this object depend on the choice of this additional data? And that will be one particular application that I can offer, in a sense, what is this good for? The connection that it offers, this label B and dependence on choice of spin C structures, has to do with yet another subject, namely cobordism theory, whose founding fathers are René Thom and Lev Pantradian. It goes back to work of many people in 1950s, such that every manifold represents a class in the abelian group, and manifolds are supposed to be in the same class if they can be connected by a manifold in one dimension higher, realizing these two manifolds as the boundaries. So this relation is cobordism equivalence relation. And as a result, we get an abelian group for every dimension D, where manifolds represent classes in this abelian group. In early days, when cobordism theory was introduced, its first examples were oriented cobordisms and frame cobordisms, which have connections to stable homotopy groups of spheres. So these are different variants of cobordism theory, which basically relate or operate on manifolds equipped with additional structure, such as choice of orientation or framing and so on. In physics literature, the most prominent or popular form of cobordism group is probably spin bordism group. And part of the reason is because this is related to classification of symmetry protected topological phases of matter with fermion symmetry. So if you have only fermion symmetry and nothing else, then the relevant group that classifies these phases, these fermionic phases, is spin bordism group in dimension D. And in particular, in D equals 2, you see that it's Z2. And this Z2 classifies two phases of Kitaev spin chain. So that's something that is quite popular, and many physicists are probably familiar with it. We were talking about 3 manifolds, so this talk is mostly about 3 manifolds. And as you can see, the spin bordism group in dimension 3 is trivial. So it may look as if there is no story or there is nothing interesting going on in dimension 3. Well, this is not quite the case, because it means that any 3 manifold equipped with a choice of spin structure can be realized as a boundary of a closed or a 4 manifold. So that's what it means to be bordered to 0. So as a result, this allows us to define an invariant of a 3 manifold equipped with a choice of spin structure as a signature of that 4 manifold whose boundary is a 3 manifold with a spin structure S. This invariant, called Rokhlin invariant, was introduced in 1952. And the reason I mention it here is that it's a nice invariant of 3 manifolds and plays an important role in cobordism theory, as I'm going to discuss in a second. So here on this slide, where I list spin bordism groups, we see that even though spin bordism group is trivial, is itself trivial, it actually opens the door for introducing Rokhlin invariant by using manifold of 1 dimension higher. But we can also make the story of bordism groups in dimension 3 non-trivial by introducing additional requirements. For example, we can require M3 to be a homology sphere and corresponding bordisms between 3 manifolds to be homologically cylinders. So this leads to so-called integral homology bordism group, which is called theta Z, Z for integral homology spheres. And unlike spin bordism group, the situation here is complete opposite. It's trivial in dimensions other than 3, but it's highly non-trivial. In fact, it's infinite. And in fact, it's not known at present what this integral homology bordism group is in dimension 3. Rokhlin invariant, which we saw on the previous slide, can be used to show that this group is non-trivial, namely the class of the Poincare sphere defines a non-trivial Z2 element. The Rokhlin invariant provides a homomorphism from the theta3z into Z2, and the Poincare sphere corresponds to non-trivial generator of Z2 in the image of this homomorphism. So then Freushov used gauge theory, Yang-Mills gauge theory, about 20 years ago to introduce another invariant, which tells us that this integral homology borderism group is not only non-trivial, but in fact is infinite. So in particular, it contains a Z-summand. And then there are some other invariants of integral homology borderisms, which are more delicate and quite popular in modern topology. For example, invariance alpha, beta, gamma introduced by Ciprian Manolescu, or so-called correction terms introduced by Osvas and Szabo using Higard-Fleur homology. So some of these rather delicate invariants, just like Rokhlin invariant, can be defined for general three manifolds. And the question is, do these manifolds, do these invariants, which appear to be quite different from anything I was describing earlier today, have anything to do with the BPS Q series? One thing that they have in common is that they get labeled by either spin or spin C structures, just like the Q series invariants that we're talking about. So in particular, it turns out that the fractional power of Q that we saw several times today, that in the case of harmonic oscillator would be basically ground state energy of the harmonic oscillator. So that fractional power is related to correction terms for each value of label B that labels the choice of the Q series. And if you take the limit Q goes to I, then you get a relation to Rokhlin invariants labeled by spin structure. So this additional dependence on spin C structure is actually quite useful. So in practice, you can check this, and that's precisely where knowing what the Q series is extremely useful. For instance, I showed you that in some examples, you can actually recognize that the answer you get is a Q hypergeometric function or function with some known modular properties. But in random garden variety examples, like this hyperbolic surgery on figure 8 knot, or you can do it for many other knots with 10 crossings and so on, what you get is just a Q series. And in this Q series, you can compute coefficients of powers of Q to any accuracy, so namely to any order in the Q expansion, but we don't know how to write it in a closed form. So therefore, if you want to check that, for example, at Q equals I, you get a relation to Rokhlin invariant, what you have to do is you have to take this rather delicate limit, and the only way I know how to do it is numerically, if nothing else is really known about this Q series. That's why I offer bottle of wine or case of wine for recognizing its properties, because other than that, you just resort to numerical analysis. And numerical analysis is also not entirely easy, because in this Q series, you see that coefficients are +1, -1, +2, -2, +1, +3, +1. So they actually oscillate in sign. And the big graph here, this orange or yellow curve, shows the amplitude that they actually grow in absolute value. That's why Q to the 500 is accompanied by coefficient 15,000. So the absolute value of the coefficients is growing very fast, but the sign is actually oscillating. So that makes the numerical analysis pretty tricky. And the smaller insert on this graph shows that if you're trying to approach Q equals I, in this case, with careful analysis, you can actually get nice convergence to the expected value of the Rokhlin invariant. So that's where knowing something about this Q series would be quite useful. So I hope I illustrated that there is this class of BPS Q series invariants that can be quickly computed and fun to play with. In the case of free manifolds, they share many properties analogous to Vafa-Witten partition functions, namely they're labeled by additional data, choice of these labels B or spin C structures. In general, they're expected to be characters of various chiral algebras, also very similar to properties of the Vafa-Witten partition function. And there are some connections to quantum groups. Many of these directions, of course, would be interesting to explore further. So that's all I have for today.
Please join me in thanking Sergei for a great talk. If you have questions, please raise your hand in the participants menu. We can start with a question from the chat from Tudor. If you can unmute yourself, Tudor, you can ask your question.
Thanks, Sheldon. Thanks a lot, Sergei. I wanted to ask if you could tell us about a precise physical definition of this two variable series. You mentioned some 3D analog of Vafa-Witten. Like why it should exist.
Right. So its physical definition would be the following. It's original. So I'll offer you two, or maybe several, and I'll let you choose which one you prefer. So there are several, and I like all of them. And I think one should use kind of combined perspective because it may shed light on different aspects. So originally, it came about as part of 3D correspondence, which of course you love, and that's going to be my first definition. So we take theory T of M3, but it's important to take the complete theory, which includes a billion connections and everything. And we compute its half index for a very special choice of 2D02 boundary condition that's associated to choice of spin C structure or element in H1 of the 3 manifold. In this case, I'm just doing it for SU2. So that's one way. And in that way, it's actually not entirely obvious that the boundary condition is labeled by spin C structure rather than a billion flat connection. As I said, these are two same thing, but undercutting and gluing, they behave a bit differently. Now, the definition, which is equivalent, or at least physically supposed to be equivalent, and that makes it clear that the choice of a billion connection is really a spin C structure, is as a Rosansky-Witten theory on a 3 manifold. So 3D correspondence takes theory T of M3 and computes its partition function on a solid torus, whereas Rosansky-Witten theory would be on a 3 manifold itself. And if we consider Rosansky-Witten theory on a knot complement and take the target space to be roughly cotangent bundle of the affine Grassmannian, we get the same invariant. And here, the variable x comes from the choice of the background. So it comes from the global symmetry, which is triholomorphic, and as a result, it can be realized as a background. We can turn general background for this symmetry or its Cartan, and that's the variable x in that story. So then there are several other definitions that are less developed, but I personally hope that they can be developed. One involves Kapustin-Witten equations on interval across a 3 manifold. So for this, we need to analyze moduli spaces, and there is some discussion of this in paper with Pavel Putrov, Kumran Vafa, and Dupay. And another definition would be by looking at this from the perspective of Calabi-Yau manifolds and Lagrangian branes in there. So formulating it as enumerative open BPS invariants in a setup, typical setup of Gopakumar Vafa and Aguri Vafa. So here are several options.
Thank you.
Sergei, that Rosansky-Witten theory has a infinite dimensional target space, if I heard right?
Yes, you heard it right. And in the paper on which this talk is based, and you can look at more for more details in the paper, we basically battle two things which were crucial in this story. One is that target space is non-compact, and the second is that target space is infinite dimensional. It turns out that infinite dimensionality is the least fearful or scary of these obstacles compared to non-compactness. So what's important is that if there is nice symmetry in the target such that fixed points are compact, then things become much nicer. And the only thing that happens in this infinite dimensional case of affine Grassmannian is that there are basically infinite sets of such fixed points. And that's why the invariant is roughly a Q series. Again, that's very rough, but that's the flavor of that story.
I don't see any other hands raised. Are there additional questions? I know, Sergei, you had asked about taking extra time, and I was a little harsh with you. If you would have taken more time, what would you have said? That's my question.
About what? Which part? Sorry.
I'm just giving you an opportunity to say more in case you rushed yourself to stay on time.
Well, like I say, there are many different aspects here, and I try to choose topics for today so that they don't overlap with other potential approaches or talks that some people might have heard, including various talks that many of my distinguished collaborators gave. For instance, the modularity aspect is certainly very intriguing, as I try to emphasize for concrete calculations. It's good to know what class of functions or what kind of Q series is this. Is it a quantum modular form or higher depth mock modular form? Even if one wants to check this relation to Rokhlin invariance, it would be much nicer if you knew something about the nature of this Q series. So, but again, that would be probably a whole different talk.
Thanks. But we do have more questions in the chat and raised hands. So, Sergei Gukov, could you unmute yourself and ask your question?
Thank you. Thank you, and thank you for the talk and explaining it so nicely. Is there ever a case where the two variable thing is in automorphic form? So the Q series from other talks, I might be wrong, in some cases turns out to be a mock modular form.
Right.
So if
a two variable thing, I have no idea. I think in some rare cases they coincide with things that Jeremy Lovejoy and other people studied. So I would say it would be some kind of Jacobi version of mock modular objects maybe, but I don't know off the top of my head, but I would imagine that maybe that direction is,
I know Greg gave a talk where he talked about mass Jacobi forms, but maybe it's something like that, although you're right, there's no generalization of mock modular forms to other groups or to Jacobi mock modular forms. So.
Yeah, this variable x has kind of Jacobi variable feel to it, but I don't know to what extent this is true. We should ask our modularity colleagues or number theory colleagues to help. I am not an expert on this. That's a great question. That's a fantastic question. I apologize that I don't have a good answer.
Thank you so much. That's great. Do you know in which particular cases the Q series is so special that all the variables are either +1, -1, or 0?
Well, I know one large class of such manifolds. If you look at ciphered manifolds with, say, 3 singular fibers, which is extremely special. Hello.
Sorry. 1 second, Saru, I need to finish it. 1 second there. I can try to turn the camera on, but she should be sleeping anyway. Sorry. Sorry, 1 second.
Go to bed.
Yeah, I have to do this. So.
Yeah, so in some cases you get so-called false theta functions. This is a very particular subclass. When you get this just plus minus ones or zeros, probably there is a bigger class, but they come in the case of ciphered manifolds with only 3 singular fibers.
Okay, and the base being 0, genus 0?
Yeah, base being genus 0. I don't know what happens. Probably, maybe the same is true when base is high genus.
Yes. Okay, thank you so much.
I actually don't know. That's a good question. In a sense, I can return the favor by asking, I have no idea why would it be significant that coefficients are just plus, minus 1 or 0.
Yeah, so there are some very special L series which have this form. They are called L functions of Dirichlet characters. So they simply come from the fact that you take a character on a finite group into Z mod 2, so 0 and 1. And so every time this is a period, I mean, you can think of it as a periodic function on integers, which is 0 whenever the integer is a multiple of n, where the character is on a Z mod n. And for and after n, it just repeats itself. So it would be, I mean, it would be very nice to, because these are the most basic L functions after the Euler-Riemann zeta function, the Dirichlet L functions. And it would be nice to see them in geometry somewhere. But I think just from looking at the few series that you presented where the coefficients are 0, 1, or minus 1, there's no repetition in the coefficients after some number, right?
No, there. Where was it? Here. Well,
so not even. I mean, so a series with the coefficients only 1, minus 1, and 0.
Yeah, so that's the first example. Somehow
Yeah.
I thought I would expand it to first few terms. I violated the rule that Don Zagier taught me, that if you ever write a series, write first few terms. So if you do this for the first example, you'll get precisely this plus, minus 1s or 0s, and they will be repeating. So there is a periodicity.
They will. Okay, great. Okay.
Yeah,
Okay,
yeah,
those should be. I would love to see more of them. So I really should go. So maybe I'll email you or we'll talk later at some point. Thank you so much, and sorry I'm gonna run.
Sounds good. No problem.
Thank you.
So I have a question from Ami Hanani, who asks if there's any relation to slices in the affine Grassmannian.
There should be. There should be, and I don't know much about this yet, but I'm extremely interested in exploring it. So we should talk.
Good. So then Andy Nysky has a question that you had an example for compact n where you wrote a Q series, and so you don't know a closed form for the function. Is it known at least that it's an actual function of Q for inside the unit disk as opposed to just a Q series?
It's an actual function. You can compute its values, at least numerically in this case, like the second example, which is currently on the screen. Yeah, so I don't know much else about it. I played a little bit with numerics of it and other similar examples, but that's precisely the reason why I'm willing to offer wine to anyone who either tells us about modular properties or anything else about this function. Honestly, I have no idea what it's good for. What kind of function is this, and yeah, what is it good for? So here it comes out as a function encoding the spectrum of states, analogous to the harmonic oscillator with this fractional power of Q in front. And all I can say about this function is precisely this fractional power of Q as a prefactor. So that's all I can say about it.
Are there any additional questions? Okay, we have another question. Do you expect gauge theory to be able to completely describe theta cube, theta 3 sub z, as in can all integer homology borderism invariance be studied by some form of gauge theory?
Sorry, can you please repeat the question?
Maybe Hank Chen, can you unmute yourself to ask the question?
It's probably about this slide or relevant to this slide.
Yeah. Hello.
Yeah.
Yeah, I was just wondering, for the group, the borderism invariance, the homology borderism invariance, I was just wondering, like, if we can use just gauge theory to tackle the entire thing, or it's rather just a question of opinions, really. But I'm just asking about your opinion.
I don't have an opinion, which is probably a good thing to have or not to have. to me, it was curious that we saw some of the standard and highly non-trivial borderism invariants appearing as limiting values of this BPS Q series. So to me, this tells a lesson that we can try to look for new borderism invariants as other limiting values of various BPS Q series. So anytime you see BPS Q series, such as this one for 3 manifolds or Vafa-Witten partition function for 4 manifolds, at least to me now, the lesson is let's look at various limiting values and ask, what does it mean? And could it potentially give new borderism invariants? And if the answer is yes, it would actually shed light on this theta 3z, because to understand this group, you really need new invariants. We need a lot more. I don't know if gauge theory will be enough or not, but we clearly need a lot more because we don't even know if this group has torsion, for example.
Right.
So there are lots of things we don't know about. Yeah.
It would certainly be interesting if we can just look at gauge theory for the entire.
Yeah, on this, I don't really have strong opinion.
Okay. Thank you.
Are there further questions for Sergei? Well, if not, let's please join me in thanking Sergei for a very engaging and clear talk. Thank you so much.
Well, thank you guys. Thank you for organizing this.
With pleasure.